Okay, first of all, so before say anything, I need to mention something I forgot to write down before, but it's something very simple to check. Is that the Bogoliubov coefficient satisfies this relation over here? This is going to be an important relation for our computation. And how do you prove it? You just use the fact that, I mean, you want, by definition, that also the F modes are orthogonal. So you just compute these kind of operators. If I out the scalar product out Fj out is equal to delta Ij. So you do that, you get this constraint. I forgot to write it down before, but it's something very simple, but it's something also very useful. Okay, so before I asked you a question, and the question was, we have checked, I've written it here, that the expectation value of the number operator in the in-state, as seen from the observer in the out region, is not necessarily zero. In particular, it's non-zero if and only if these beta are non-zero. And then we have discussed that if the space-time is stationary, then beta are zero. So now we're going to discuss Hawking radiation, which is the particle emission from black holes. Does any of you have any idea of how is this possible? Of course, this is what we're going to answer in this class, but if you have any idea, especially people that are already a bit familiar with Hawking evaporation, it would be nice to discuss your ideas. So, anyone that has some thoughts, even not an answer, just a thought on this issue? How can a static black hole evaporate? Yeah. Mm-hmm. Okay, so Atabax is referring to the standard picture in which the vacuum is not vacuum. You have a particle and antiparticle. If they are created near the horizon, one can go toward the singularity and one can escape. Probably most of you, if none, have heard this explanation, and it was also written by Hawking itself. So there are some good points in this explanation, but I hope I will convince you at the end of this class that there is a lot of shortcomings in this explanation. It does not capture the main physical property. But thank you for the answer, because that's definitely one answer used like the possible answer, but we will see that this is not does not capture everything. It captures something, otherwise Hawking will not have written it. But yeah, I mean, this is the type of explanation you are allowed to give to your grandmother that asks you how does a black hole evaporate, right? But not to quantum gravity students. So any other guess? No? Okay. So the question was, how can static black hole evaporate? Ah, yes, the mode function in asymptotic past and asymptotic future will be different. In that case, beta coefficient will be non-zero. I mean, this is true, but how is it possible if the black hole is static? So, the question, how can a static black hole evaporate? Answer, it does not. So, static black holes do not evaporate. We will see tomorrow what happens with static black holes, but they do not create particles and emit particles. So what is Hawking evaporation? I said before, black holes are not eternal objects. Black holes are formed by gravitational collapse. So Hawking evaporation, we are going to discuss it now. We need a gravitational collapse. And as I mentioned, I want to discuss the simplest possible scenario. So I'm going to discuss the simplest possible gravitational collapse. which is a single null shell creating a black hole. So, I mean, I draw the Peros diagram of a collapsing black hole before. That could have been a hint. We're not going to discuss now the eternal geometry. We're going to discuss it tomorrow. So this is the Peros diagram I drew before, right? And before I draw some region, which was matter region, I didn't know the geometry inside. And this is actually how Hawking did the computation without specifying the geometry inside the matter. And we were going to explain why you can do that. But in order to remove all the difficulties, we are going to specify the matter which is creating the black hole, which is a single null shell. So the single null shell at V equal V naught. Okay? So then we have the event horizon. This is the event horizon, as I mentioned before. And then we have all the other points important. I minus, I naught, I plus, I plus, I minus. Okay? This is the simplest possible scenario, so that everything non-trivial is actually what is causing Hawking evaporation. And so what is the geometry of this spacetime? We are going to have two regions, right? The region outside the shell, let's call it region, well, out, because we are discussing out and in states, right? And the region inside the shell, which is the in region. The geometry in the in region is Minkowski, because there is. So basically the geometry in this spacetime is Schwarzschild with the mass as a function of time, and the mass is 0 before V naught, and it's m, the mass of the shell, after V naught, right? So the geometry, the square in the in region is equal to minus, I don't know, let's write it in the t r component, the t in square plus dr square plus r square d omega square. I added in specification here because the time can be discontinuous across the shell, but I didn't add it here because the radial value is continuous. This is the Israel junction condition. If you're familiar with it, okay, you've seen it. If you're not, it's fine. Just the result is that the metric induced to the shell is continuous, so the radius is continuous. So I don't need to write out and in. And then I have the geometry in the out region, which is Schwarzschild. Minus 1 minus 2 g m over r dt square out plus 1 minus 2 g m over r. So d r square plus r square d omega square. Okay. And so now that we have the background geometry, we put a quantum field. And before I did all the discussion with a massless scalar, so this is going to be the field equation that my massless scalar satisfies. Box in one region is going to be evaluated with the flat spacetime metric, in the other region with the Schwarzschild metric. And so what we need to do is clear. We need to define the modes in the in region. We need to define the modes in the out region. We need to somehow compare the two, and which is the question that you asked. If they are in two different regions, how do we perform the scalar product? And then we do the scalar product. Okay. Yeah, so the in region is going to be very, very, very far in the past. Of course, yeah, if you have a null shell, this kind of spoils because the time dependency is never here. But what I'm going to define as in region is observer living on Scry minus, and out region observer living on Scry plus, right? And of course, if you take observer on Scry minus, then then if I give initial condition like here and then evolve, this covers the entire space-time. Right? Scray plus does not, because there are modes that do not arrive to Scray plus, right? And there are modes that go inside the black hole. So I am losing some of the modes if I only focus on Scray plus. And there is a problem that the modes that go towards the black hole, they are not in asymptotically static region. So it's difficult to define modes here, also not asymptotically flats. It's not so obvious. I cannot just use plane waves I'm going to do. But for the purposes of static radiation, what is an observer on Scray minus seeing and what is an observer on Scray minus plus, I don't need those modes. But keep in mind that we are going to lose some modes, right? But this is unimportant now. Okay. So I've written the geometry in these coordinates, and I can now write down the field equations, and I guess that you know how to do this. Like you take the scalar field, you expand it in base of spherical harmonics. M y Lm over R y L M. Right, this is spherical harmonics that depend on the angular components. And these are depending on, let me write just T and R. But of course, T and R are, the T is different in the two regions, right? So this is either T in or T out. And now you can do the computation and expand this box phi equal to 0. And what you are going to find, if you do it, is that in the Minkowski region, yes, Rava. Uh, no, actually, no. I'm going to do, and I will go back to UV coordinates. I will explain the coordinates. But anyway, I'm only quantizing near Scray minus and near Scray plus. So it's asymptotically flat. So, yeah, in the linear algorithm of the GM, it's difficult. I will not care about it today. What I want to compute is a relation of observer living here and observer living here. Okay? Great. Now, if you do that, let me know. Let me check because I might make a mistake. Well, I cannot find it, but anyway. Yeah. So in the Minkowski region, you will find like the phi LM. Later, I will drop the LM labels. The T square plus the square phi LM the R square plus, and this is what I wanted to check because I never remember the angular part, but I think it's R square here, right? And then well, it's minus here. And then you have in the Schwarzschild region phi LM the T square T LM the R star square. This is the tortoise coordinates that we have introduced before. I mean, I'm not doing the computation, but you can check it. Plus 1 minus 2 GM over R R L plus 1 square plus 2M over R cube, maybe. So yesterday I prepared some notes to check this kind of stuff, and then I left it in the hotel. So that's why um, there is definitely G. I don't know if it is the only thing that changes, but it's definitely G. Huh? Bye. Yeah, I mean, I was so worried about this numerical factor that I forgot the things that I should have been able to remember. Anyway, there could be a different numerical factor. Huh? It's fine. Yeah. Now I'm going to do a very crude approximation. Then we will go back. And the approximation is that I will forget about the potential terms. Right? Then I will just explain what happens if you add the potential terms, and I will tell you how to do the computation. But this is just changing some details that are not captured in the core of the effect, right? So I'm just considering really free waves in this spacetime. So you can see the ingredients here are almost nothing, but still we will get something which is very non-trivial, which is actually extremely interesting, right? Because it's like extremely simple setup, but then you get an extremely non-trivial result. This is R. Yeah, thank you. Okay, so given that we are just well, asymptotically, I mean, this next step actually does not depend on the fact that we are dropping this. You can see asymptotically this term vanishes. So the bases that we choose asymptotically are just the plane wave, and then they have a combination t plus or minus r and t plus or minus r star, which are exactly the UV coordinates that we've described before, right? So we have the in modes that have in omega. Let's focus on Scray minus. So on Scray minus, we only have left-going modes, right? Which are modes. Yeah, we have left-going modes that then they can reflect at r equals 0 and reach Scray plus, or they can reach the singularity, right? So a base of modes in this region is just equal to, and also because we have the in both regions, is just equal to e to the minus I omega v, where v is the coordinates on Scray minus, right? What are the out modes? As I said, the out modes should include, if I want a full base, not only the modes that are originated, like not only the left-going modes as on Scray minus, right? I should get the right-going modes on Scray plus and the left-going modes at the horizon. At the horizon, I don't know how to write them. But as I said before, if I'm only care about what an observer Scray plus is, I can forget about them. I will just focus on Scray plus. But keep in mind that we are losing some information. We are losing all the modes that go into the horizon. So the out modes, f omega out, are just equal to e to the minus I omega u, the coordinate of Scray plus. And now we need to add I need to add a descriptor out. Why? Because I choose v, the coordinate of Scray minus, but t is discontinuous. So also u, the u coordinate, is going to be discontinuous. Okay? So I've written here the geometry and the t in and r coordinates, but then I'm going to work extensively in the uv coordinates. And v is just this the coordinate here, so it's continuous of the shell. U is discontinuous, so you need to take into account the fact that u is discontinuous. And that's why I add it out. Now, these are the modes, but I want them normalized. So I need to add the normalization factor. If I'm not mistaken, this is 8 pi omega. 8 could be wrong, but pi omega are correct. Even if 8 is wrong, doesn't change anything. Also because we're not going to perform the final integral exactly, so it doesn't matter. I mean, I'm just giving the result of the final integral. I'm not going to do the integration. Okay, so we have this base. We need to do the scalar product. Right? We want beta. Beta, omega, omega prime, right? Before the index were ij, now the index are omega, is the frequency of the wave. Which was defined as the scalar product of I deleted it. Yeah, it was minus f out omega f in omega prime star. So this is what we need to do, right? And actually, we're also going to need alpha. In principle, we do need alpha, but it's going to make the computation simple to know also the value of alpha. F omega prime out f. Okay. And then I wrote before the definition of the scalar product, and actually, as you pointed out, I didn't write it. I mean, I wrote it for flat spacetime, but what we need is the like we need it for generic spacetime, right? So what we need to do is to take an hypersurface sigma mu, so the sigma mu contains the normal vector, right? And then we have phi one, the mu phi two star minus phi two star, the mu phi one, right? This is the correct one. Yeah, apology, and thank you for pointing it out before. Now, given that this is conserved uh, by the uh, by the dynamic evolution, I can choose this separate surface as I want, as long as it takes the modes that I'm interested in. Right? So this means that I could take an upper surface. I'm losing the modes that go to the horizon, right? So, but I can take some upper surface here, here. I will take square minus as my upper surface. Right? It's not technically a Cauchy upper surface because it's time. It's null. It's not space-like. But I can still define the products on this Cauchy upper surface, even just taking the limit procedure. So what I need to do, I need to perform this integral with this definition on the Sandler surface square. So for instance, beta omega omega prime is going to be equal minus goes away. So it's going to be I, the integral on cry minus dv equal to square minus r square, and then we are going to have f omega out dv f omega prime in minus star minus f omega prime in star dv f omega out. Okay, so we almost have all the ingredients. But we know f in, and then we go back to your questions again. We know f in on square minus. What is f out on square minus, right? We don't have f out on square minus. And so f out has this expression, but on square plus. So what we need to do is to trace it back on square minus. And this is the step in which all the simplification I've done simplify the job. So removing the potential, considering a null shell, this step is very easy because of that. But this is not, I mean, this is I mean, we will discuss what happened when this, I mean, what changed when I consider all this other complication, but the core of the physics is not there. Yeah. The point is that the ingoing, so yeah, I mean, the outgoing part is not on screen minus, right? And this is why this is not a Cauchy-Shepard surface, because it's not taking the outgoing one, right? But anyway, the outgoing for consistencies are just the reflection along r equals 0, right? And also they just go to scrape plus. And so I mean, so the point is that we are taking all of the modes just by considering the the ingoing on screen minus. Because we are not missing anything, because all the right going, they all originate on screen minus, right? If we had the I will draw here, then I delete. If we had the eternal black hole geometry, then it's not enough to take mods on screen minus. Because the mods on screen minus just, do this. But all the right going modes, they don't cross screen minus, right? So if we consider when we consider the eternal geometry, we will see that, we will also need to consider the right going modes. And actually, we cannot take screen minus as the good hypersurface because it does not contain those modes. But this we'll see tomorrow. And this will be the second answer to today's question, because when I say static black hole do not evaporate, it is true, but there is still something non-trivial going on, and that we'll check tomorrow. Yeah. Yeah, exactly. So the original king. Yeah. No, in order to have a non-trivial result, you need a reflection. Well, of course, also in the eternal geometry, you need dynamics. Sorry. Also in the eternal geometry, there is some stuff that are interesting, and we will discuss them tomorrow. But particle production, it happens in the dynamical case, and this is actually, I mean, this is very similar to Hawking original computation. What Hawking did was, instead of considering a null shell, he considered just a star generic generic metric is the star, and so the fact that it's generic makes the computation more complicated. But as I will try to convince you without any computation later that there is a universal behavior late time, and so the result is actually the same. But yeah, Hawking computation you just include this case, but it's just this with a small yeah, a small. What? Of course. But of course, because this is, I mean, this is of course true because you, because you, yeah, yeah. No, what do you mean? I mean, like the exterior geometry is Schwarzschild. So, no, wait. The total manifold is time dependent. The geometry on scale minus is static. The geometry on scale plus is static. But the fact that you have a time dependence is really crucial. Yeah. Because no, it's not static limit. I mean, the point is, I mean, this is the horizon. So we will see the modes that they will be relevant are the modes that start here and reflect nearly close to the horizon. Yeah. Yeah. Of course. Yeah, of course. Because here in geometry is static, but not the full manifold. So if the black hole is not formed by gravitational collapse, you don't have creation of particles. Yeah. Yeah. No, I agree with you then. Absolutely. Exactly. And this is what we discussed before, right? What you want to do is to define a need state where it's static, out state where it's static, and the dynamics in the middle will give you some non-trivial property, but everything that you do, the mode quantization is static. Yeah, yeah. Okay, so what I was saying, yeah, we just need to trace back the mode from scrape plus to scrape minus, right? I will draw another diagram because that's starting to get to look messy. Uh, okay, so we have the null shell here. Uh, Note that the eventor at v equal v naught. The event horizon, it starts in this point here at v equal v horizon. We will compute the value of the horizon, but note that this is well before the shell. So the event horizon starts here, where no causal, there is no causal way to understand that this is a shell. And so this is what I was saying before. The event horizon, I mean, the geometry here is Minkowski, but we are inside an event horizon, right? But this is one of the cases where actually the event horizon is relevant. Um, so we had the modes defined on square plus. We want to define them on square minus. So how do we do that? Let me. So these are right-going modes, right? So the modes start from square minus, they reflect on r equals 0, and they arrive on square plus. So if I start from square plus and I trace them back, well, let me draw. This is a mode. It's not a geodetic, but let me draw like trace them back. They reflect on r equals 0, and then they arrive on square minus, right? So we're interested in the modes in a few points. Maybe I can denote with the blue marker. Let's say 1 here, 2, 3, 4, 5, and 6. I will tell you what are these points now. So the point 1 is the point where we know the result is on square plus. Okay. Then we need to trace it back and arrive up to the point 2, which is at v equal y naught plus epsilon, which means just outside the shell. But then we need point 3 at v equal v naught minus epsilon, just inside the shell. Well, sorry. 2 is just in the future of the shell, and 3 is just in the past of the shell, not inside and outside. And then we need point 4 at r equals 0. Well, not at, near r equals 0. Near r equals 0 in the future. Then we need 5 near r equals 0 in the past. And then finally 6 at on cry minus. And once you do 6, we can do the integral. I mean, you can do the integral. We do together these 6 steps, then I give you the result of the integral. I don't want to do the integral with the blackboard. I don't know how to do integrals. Yeah, I don't know how to turn into a differential equation. I don't know how to solve differential equations. So I'm more an astrophysicist, to be honest. Okay, so this is the plan. Any questions? The questions is scary. Okay. Okay, so I will also add, so to make it clear that you have 1, 2, 3, 4 points, I will add an index, but it is not, I will get rid of it once we finish. So F omega out 1, so on square plus. This we have it. This is how an observer on square plus will split the positive and negative frequency energy modes. So this is equal to the one that I have written there. E to the minus I omega U out divided by the normalization factor. 8 by omega. Okay. And this is easy. Now F omega out omega 2. To do that, you need to trace this mode back using the wave equation. Now, if we used this wave equation, the mode will look a little bit complicated, and near the horizon, well, but this is not, yeah. When we will focus on near horizon, then this does not really matter because this is 0. But in the way from square plus down to the point 2, the mode will look differently, and in particular, some will be back scattered. But given that we forget about this potential, we don't need to do anything. The mode on the point 2 is just equal to the mode of point 1 because you have just free wave propagation, right? So this is just equal to F omega 1 out. Simple. Now we need a slightly less trivial step, which is to relate point 2 and point 3. Very close. Yeah. This is epsilon going to 0. So it's and this is also very near r equals 0, and this is just a reflection. So what I'm saying is that the wave propagates freely from 1 to up to the shell. Then at the shell, I need to use the junction condition to understand how it is at the other side of the shell, and then it keeps propagating freely. It reflects at r equals 0, and it keeps propagating freely. It's because we deleted the potential term. No. It's point 1 and 2 are very far away. But you see, this is a free wave equation. So if you just consider the time evolution of e to the I omega u, this is just e to omega u everywhere. This is just plain wave propagating freely because we forget the potential. Okay. We will see later that the most of the effect happen near the horizon. So this is a good approximation, but it's exactly from point 1 to point 2 that something non-trivial happens, and this in fact give a correction. Okay, so the result that we will obtain will not be the final result. We will need to be corrected. But yeah, so for L equals 0 it's actually very similar because for L equals 0 this is the minimal, right? The minimal modification because you have only a small term here. But generically, yeah, there is some modification. And in fact, if you take the result and just trust the result, and you want to compute the total luminosity, that will be infinity because you need to sum over L, and for L is very large. This is a very bad approximation. But I will just give you the final result. This is just the simplified setting. Okay, so now we need from 2 to 3. Just in the future of the shell, just in the past of the shell. Let's do it here. So in the point, let me also show the diagram. The point 2, the metric is Schwarzschild. Point 3 is Minkowski, and we just need. So in the point 3, what we need to write is u out in terms of u in, Right? So we need to, this is going to be e to the I omega u out, but expressed in the new coordinates, in the coordinate of the region in. Why? Because we are assuming that the scalar field is free, so there is no interaction with the shell, but we need to write it in the proper coordinates. Right? And so how do we? So we just need to find this u out as a function of u in. So let's see how to do that. Okay, so u out is it was defined as t minus r star. We've seen this before. And also we have v, which is the same, which v is continuous assumption, as t, and it is out. So that t is discontinuous. T out plus r star. And if you remember before, we wrote r star equal to r plus 2gm logarithm of r over 2gm minus 1. What about in the in region? In the in region, we have u in. This is Minkowski, right? So it's just t in minus r, and v in is equal to t in minus r. And as I mentioned before, the junction condition of the shell tell us that the radial coordinate is uh, um, is continuous at the shell, right? Hmm? Thank you very much. Thank you. And so we just we can, in order to write u as a function of u in, we can just eliminate r and in terms of u in. Sorry, and in the v coordinate is not required because the v I choose the coordinate that you know I can choose that continuous at v. So v is equal v naught, and this is v in the in region, and v greater than v naught is in the plus region. So at the shell, if I just do this minus this, at the shell I have that u in minus v naught, the value of the shell, is equal to minus 2r. And also from here, I don't have space there, but let me write it here. I get a very similar relation. U out is equal minus v naught is equal to 2r star. And so I can just then r star is given by this, and take these two together, which will give me u out as a function of u in. And so what does this give me? This gives u out is equal to u in u in plus 4gm logarithm of u in no minus u in plus v naught minus 4gm divided by 4gm. I have done in my head, so there might be mistakes. So let me check this result. U out is equal to u in. Yes, there is a mistake, and it is this is minus. So there is a minus here. Okay. So we can write down the mode in position 3. Position 3, yes. F omega 3 out is equal to, let me write it like this. So exp of minus E omega and then U out, but I need to write U out in terms of U in. So it's U in minus 4gm logarithm of P naught minus in minus 4gm over 4gm. Okay, perfect. Let me also mention that from this relation here, we can actually find the value of V horizon. Because V horizon is this point in the Minkowski region, and in that point r is equal to 0. And so for V horizon from this relation, so for r equal 0, you have V equal U in, right? And U in at the horizon is the value in which this diverges, right? Because the horizon is U out going to plus infinity. And this also shows something different, that this diverges when U in is perfectly fine. So the horizon in the Minkowski region is perfectly fine location. You will never mention this. So the horizon in the U in coordinates is at U in equal V naught minus 4gm. And so VH here is exactly V naught minus 4gm. This is just, we can actually compute the value of V naught. All right. So we have the F out omega in the point 3. And now we go again, pre-propagation up to the point 4. Again, because I removed that term. Pre-propagation up really close to r equals 0, but in the future. And so this is F omega 4 out is just equal to F omega in the point 3 out. And now we need to consider the reflection across r equals 0. And yeah, to do that, we just know that right going and left going modes, they change into each other at r equals 0, right? So we just need to replace V and U in. We just need to invert them. Hmm? I mean, the new expression is omega 3 out. It's not a plane wave anymore. No, it's still a plane wave. It's just a combination of outgoing and ingoing modes, and this is exactly what's going on. So it's still, yeah. So not outgoing and ingoing modes. It's still a combination of positive. It's just a combination of positive and negative frequencies. So it's a completely non-trivial combination, but it's still a solution of that. Okay. Thank you. Yeah, that's a very good question. And also look here, I have the absolute value of no, okay, let's do first the reflection. So when we do the reflection, just U in goes into V and vice versa, right? Because left going modes become right going modes. And so plus it's completely not important in this case, but to be like precise, you do get a minus sign because when you do this in the Minkowski region, you do this expansion here. The regularity implies that pi goes to 0 at the horizon. Sorry, at the horizon, at r equals 0. So the total modes, the sum from of left and right going modes at r equals 0 is 0. So phi lm. Well, phi, I deleted I didn't tell you, I deleted the L and M dependence because I dropped the potential, so there is no dependence anymore. Phi at r equals 0 is equal to 0. So means the sum of left going and right going modes is 0. So the coefficient is -1. And so when we now so f omega 5 is equal to minus f omega 4 out, in which u in is replaced with v. And we can write it down. So it's equal to minus x by omega minus e omega u, sorry, v, this was in, minus 4 gm logarithm of v naught minus v minus 4 gm divided by 4 gm. Okay, and now note that v naught minus 4 gm is just v horizon. So I can rewrite here just to simplify this. Is so this plus this is v horizon, right? So I can rewrite this as vh minus v. We have the point at 5, and now we have to go to 6. Now this is again just free propagation, but also let me note before writing the final result is that all the modes that reach Scray plus, so that I can trace back from Scray plus, they are all with the v smaller than v horizon, right? You see? So the modes that are minus infinity, they go to minus infinity here, and the modes that that start from here, they arrive still at v asymptotically approaches to v horizon, right? But there is no mode that is traced back at v greater than v horizon. This is because if a mode starts at greater than v horizon, it ends up in the singularity. So I can get rid of this. So in the final result, yes, now I can write it. So for v smaller than v horizon, this is just this. And so I have f omega 6 out is equal to minus exponential 8 by g minus e omega v minus 4 gm ln v horizon minus v over 4 gm if v is smaller than v horizon, and 0 if v is greater than v horizon. Okay, we finally traced successfully the modes from Scray plus back to Scray minus. Let me check the final result because it's possible that there are some computational mistakes. Well, I don't. Yeah, okay. Yes. Mhm. Okay, this is a good point. It's not, I mean, it's ill-defined if v exactly to vh, because it's basically Scray plus infinity. It arrives to vh, and you get an infinite phase. Luckily, when you perform the integral, this does not really matter, but it's not well defined at v equal vh. Yeah, that is a very good point. Thanks. Any other question? I might do that procedure on RNT actually because they are well defined. It's just easier to do with V and U, just because I'm doing the integral on the square minus, and so you see I'm just doing the derivative with respect to V, so it's just easier. But actually, given that I'm only taking into consideration stuff that are outside the horizon, I could actually do that. But it's also true that for other questions, like if let's say that you want to understand what happens to the mod that enter the horizon, then you should change coordinates. So it's just easier to start with coordinates that are well defined everywhere. And I mean, there are questions that are interesting to look at the mods that enter the horizon. They're just more complicated because there is no precise uh, way to define the mods. Yeah, thank you. Okay. Any other question? Okay, so now, if there are no other question, you can just do, yeah. Oh, this last formula concerning, yeah. By the way, someone said, I reply, a real black hole from collapse. So this was the correct question, so the correct answer in Zoom. So someone on Zoom uh, correctly answered the question. Um, yeah, Michele Nardelli, I don't know exactly what you uh, yeah, that's the point. I don't really know. Yeah, if you write what exactly what you mean, then we can answer. Okay, so this is all the preliminary ingredients you need to compute alpha and beta, and now you can compute alpha and beta. Now, why do you need also alpha? You just need to care about beta. Is that if you do these integrals, which I'm not going to do, you can. I mean, you can solve the integral in terms of gamma functions. These are going to be Gaussian integrals, but also they are purely imaginary. So it's like the usual trick. You need to add an arbitrary small real part to regularize them, and then do the limit and reduce it. Anyway, not going to do that. You can find that alpha omega omega prime, the absolute value, is equal to e to the 4 pi g m beta omega omega prime. You do both alpha and beta, you get that result, right? And now once you do that, uh, you can make use of this this relation here. Now, of course, as you might realize that omega and omega prime are continuous indices, and it is discrete. So you can define the continuous version of this one. You will have integral on the omega, then you have the analogs of this one, and you will get the direct delta omega minus omega prime, right? This is just schematic. If you do that, uh, you get a divergent result. You get infinity. The reason why you get infinity is that we are considering plane waves on a black hole, which is emitting particles, but we are not considering the back reaction of those particles. So the mass of the black hole does not change, which implies that you have an infinite flux. Because the flux is, I mean, you have a finite flux, but for infinite times. So in total, you get something which is infinite, right? So there are several ways you can do to make sense of the infinite result. One is just that you will get this result will be multiplied by delta of 0. So you just take the prefactor. The infinity is whatever. And the other one is that instead of considering plane waves, you consider wave packets, which is I think it's the best way to do. You just consider wave packet. So when I write down this alpha and beta from now on, I'm not going to do this in detail. But what I mean are not plane waves with factor alpha, omega and omega, but they are wave packets peaked at omega and omega, right? And so I can use the discrete sum, and this gives us a finite result. But actually, before using this, so this is the result that we obtain, right? But actually, oh, well, okay, I need to say something first before writing that equation. Forget for a second that I wrote that equation. Um, Sorry about that. So this is the result we were looking for. Let's look at this result in different regimes. So one regime is for where can I delete? One regime is at very early times, which means very early U out. So doing always the same diagram. Let's say close to here on square plus, but a low U minus. This is reflected into very early times for V. So the logarithm you get so this term vanishes, and you only have this I to the I to the I omega V. So here early time F out on omega 0.6 on square minus is very similar to the normalization factor e to the minus I omega V. What does it mean? That there is no particle production. At early times, there is no particle production. Nice. At very late times, when V is similar, is close to VH, you have some very non-trivial mixing of modes. So late times, F omega 6 out is 8 by omega x minus I omega VH. We can approximate that. And then we have the logarithmic term that is the non-trivial dynamic for mg log of VH minus V divided by 4G. Okay, so at very late times, you do get something non-trivial. And this is the regime that you are going to focus. So if you do that, you can do the integrals and you get these results. So apologies if I wrote this result from to start with. This result is only true at late times when you do that V equal VH here. Okay, and now we can use this formula here with that one. And yeah, again, it might be not so nice to see sum over omega, but this has in mind what I was mentioning before. Yeah. Yeah, actually, I don't think it's like not. It's extremely difficult for care because I don't really know how to form care dynamically. To be honest, like I don't know. Um, yeah, I don't know a geometry which is a gravitational collapse, and I can describe the interior geometry somehow that I know, and the exterior is care. It's very difficult. It's not simple. So yeah, this computation for care is not straightforward. I don't really know, honestly. I've never seen that. To my knowledge, in this way, I don't think so. But of course, there are right no, there are other ways to recover this result. But this is the one that has the clearest interpretation, and I really don't think it's being done for care. I would be very surprised. So now I write this relation here with I and j equal, but actually equal to omega. So the sum over omega prime of alpha omega omega prime minus beta omega prime is equal to 1. Okay? And now I can use that result there. This is alpha square and beta square. I can use that result there to write so, so I have a prefactor which is omega prime independent, which is e to the 8 pi g m minus 1 sum over of beta omega prime squared, the sum over omega prime is equal to 1. And so the sum over omega prime of beta omega prime squared is equal to 1 divided e to the 8 pi g m minus 1. This is equal to, we have decided before, this is the point of computing the Bogoliubov coefficient, the expectation value in the in state of the number particle operators defined in the out state. What is that? This is the Planck spectrum. This is the expectation value you would expect from a thermal body. Does it mean that the emission is thermal? Not yet, but the expectation value is, so the spectrum is Planckian. And we can also read out the temperature. So first of all, let me check that the coefficients are correct. Yeah. So what is the expectation value? What is the Planckian spectrum? Because this is, I mean, we are talking about a scalar field. If you do that for fermion, you will get different sign there, but for scalar field, we get to use that the one that we will expect from a thermal from a Planckian spectrum is 1 divided by e to the omega kappa Boltzmann e minus 1. It's exactly the same, where t is equal to, now let me put back all the units, h bar and c just for now, h bar over c cube divided by 8 pi kappa Boltzmann gm, which is an amazing equation. It's really, I mean, it's an equation that includes h bar, c, kappa Boltzmann, and g. There is obviously an omega missing, yes. Yeah, I don't know if I wrote it correctly there, but yes. Okay, so the spectrum is Planckian. Let me see how much time I have. 22 minutes. Not too bad, not too bad. Okay. Yeah, so this is the expectation value is it is exactly a Planckian spectrum. And so I can define this as a temperature. Before saying that the spectrum is Planckian, we need something else that we will do later. But this is the same spectrum as a thermal body emitting at this temperature. I mean, if you take two, they have the same spectrum. Now we need something else. But let's first, so, I mean, it's instructive to put some numbers here. I mean, we are physicists, so it's good to put some numbers. But for, I mean, I'm not going to do that because, I mean, this will be, I mean, this is one usually, so it's difficult to put numbers now. But if you compute the numbers, if you put the value of the constants, you get 10 to the minus 7 the mass of the sun, just renormalizing the result to the mass of the sun over the mass of the black hole, Kelvin. Right? So for a solar mass black hole, this is extremely tiny temperature. It's way smaller than the TMB, for instance, extremely tiny, but still it's there. It's nice to know it's there. And for very small black holes, this can be much larger. Okay. Any question? No questions. Okay. Um, okay. So we said that the spectrum is Planckian. What else do we need to say that this is a thermal distribution? We need, yeah, 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 yes, perfect. And of course, I mean, there are other stuff, but I mean, there are other issues that we will see tomorrow for stationary spacetime, purely static spacetime, but this is, yeah, today's lecture. And so what else do we need in order to understand that the temperature is thermal, the spectrum is thermal? It's not only the spectrum, it's also all the higher expectation values. So thermal radiation is uncorrelated radiation. So you need to show that stuff like in and omega out and omega prime out in, this is equal to in and omega out in and omega out, omega prime out in, for omega different from omega prime, right? This is something which is true for a thermal spectrum, not for any Planckian, so for a thermal radiation, but not necessarily for any Planckian spectrum, and so forth for any other expectation values. So at least this is something that you could check, and the way to do that is uh, expand this as with the Bogoliubov coefficient. So the sum alpha A in plus beta A out, and then you will have 4 of these terms, and then you will need to rearrange them using the commutation relation, and then you will need to perform some integral very similar to the one that we computed now. If you do that, you obtain this result. We are not going to do that, but the first step is very simple. It's exactly the same that we have done here to arrive to this relation. You just need to plug 2 operators, but it's exactly the same. And then you get some integrals which are very similar. It's no longer going to be just beta omega square. It's going to have also terms depend with alpha. And if you do it, you get this result here. In principle, you could do it for any arbitrary number. And honestly, I only did it for 2 and myself, but I mean, people have done much higher. Okay, so the spectrum is actually thermal. It's not only Planckian. Like the radiation is thermal, not only Planckian. Now, in the remaining 17 minutes, I want to say a lot of things, but without equations. So it should be okay. So what I want to discuss now first is what is the role of the potential. What are the role of the potential terms, right? This one that they were not here, the one we discarded. We only took free propagation. Then different collapse. So what happens instead of a null shell, we take any star, any more realistic star. And 3, what was the role of the horizon? So in particular, what the horizon does and what the horizon does not do. And that's it. No, or did I want to say something else? Okay. Yeah. Okay, 15 minutes. So let's start from the role of the potentials. So most of the analysis, I mean, the result, and okay, will the result be the same if you had complete expectation value of n in out vacuum? Yes, it will be basically the same. So just saying that the two vacuums um, are not the same. Now, of course, physically it doesn't really make sense to do that. I mean, what physically makes sense is to start from vacuum, have a collapse in geometry, and see what happens in the asymptotic past, in the asymptotic future. But of course, mathematically, you can do the other way around. It should be the same. Or yeah, I mean, very similar. I never done the computation, but you will get something very similar. Okay, thank you for the question. So, what is the role of the potential? So, the role of the potential is that when we were tracing, we had free propagation. Now we are not going to have free propagation anymore, but some part of the of the of the of the of the of the wave of the modes will be backscattered, and this is actually the fact that we focused on very late times where we had very high blue shift, which means we focused very close to the horizon. So very close to the horizon, the potential was actually zero. If you remember, the potential in the Schwarzschild region was 1 minus 2 mg over r times something else, right? So very close to the horizon, we don't have that. And the fact that we had this very large blue shift, we also arrived on Scray Plus with not zero frequency. The wavelength is one is order of magnitude of the temperature, right? So it's order m, or inverse of the temperature. It's order m. So which means that we had started with a very high frequency. So if we trace back, those modes here were very, very highly energetic. This is sometimes go by the name of Transplanckian problem, which is we are working on semi-classical approximation, but we get extremely high energetic, extremely high frequencies. So we kind of go out of the model. But I mean, there are some arguments to say that this can be resolved, but that's actually I think it's still an open problem. But within the model, this is what happened. And within the model, actually, this simplifies because it means that all the initial propagation from Scray minus to the horizon, it can be done in the geodesic approximation. And the fact that it can be done in the geodesic approximation implies that the role of the terms we replaced, if you do things correctly, you can take them into consideration, does not really matter. And also the different collapses give you a late time, give you something which is universal because you can use the geodesic approximation. So, and also the star is basically frozen in the main time you go in and out. So this is how you can do, I mean, you can do the computation in more generic cases, but the late time is going to be universal because you can use the geodesic approximation. So basically, this computation simplifies and becomes universal. I'm not going to do it, but this is what happened. And then the potential, as I said, in the first part, when you go from Scray minus up to very close to the black hole, because you use the geodesic approximation, the potential are kind of irrelevant. They do not contribute. But then when you get closer to Scray plus, so radius much larger, you no longer are in the super Planckian regime, so you need to consider the backscattering. And so part of the waves, outgoing waves, will be reflected by the potential and will go inside the black hole. So this means that if the spectrum will not be fully thermal, and omega out in, but it will be like omega 8 pi gm minus 1, but you will need to add this term, which will be a function of omega and also the quantum number L, which is the transition coefficient. So you have a potential barrier where you go from V R, from R equal to M, this goes to 0, and at infinity goes to 0, but you encounter a potential barrier, and so part of the waves will be backscattered and fall into the black hole, and you will lose them, and the other part is just the reflection coefficient, the transmission coefficient. So the spectrum will not be truly thermal. It will have something which goes by the name of black body factor. Gray body factor. Thank you. It will be still uncorrelated. Yeah. So the point is not truly thermal because it's not Planckian, but it's exactly the same spectrum that a thermal source will emit at infinity if you do not change the potential. So in this sense, it's still thermal because even if you put a thermal source at the horizon, like in place of the black hole, if you just remove the black hole and put a thermal source, it will give you a thermal spectrum without the gray body factor. But if you put a thermal source without changing the potential, you will get exactly this, because some part will be backscattered, right? So in this sense, it is thermal, but you do not really see a Planckian spectrum. Yes, that's still also. It's still non-correlated, yes. And so what is the role of the horizon? So the role of the horizon is not to do what Atabak was saying before, that you divide the modes and then one falls into the black hole, the other does not. I mean, in part it does that, but it's less trivial than that. I don't know how many times I draw this diagram. So at the horizon formation, the modes that are correlated here are at very short distances. Sorry, this is not the horizon. This is the horizon formation. The modes that are correlated here at very short distance, they can be split by the horizon, and so some part of it will end up at Cray plus and some part of it into the black hole. But the point is that you cannot really define a particle here, and also the fact that the truly reason why you're emitting is that you have a dynamical geometry. In fact, you will have Hawking radiation even for a collapsing geometry, even if you don't form the black hole. The difference is that if you don't form the black hole, you will have a radiation for a given time, and then the radiation will stop, because at some point you will go to the vacuum, like everything will relax, and you get a static geometry, right? So what the black hole does, so what this does not do, it does not create energy out of nothing. But what it does is to translate the dynamics that happens at early times. It translates it up to infinity, because modes take infinite times to arrive here. So what it does is actually it's making things universal, and at very late times you still see the effects of the dynamics, even though the geometry is basically static. And in fact, if you plot the temperature over time, coordinates on Scray plus, U out, if you say that this is the temperature of Hawking that we computed, remember we computed it in the late time. So late time, it approaches here, and this is universal. At early times, we say there is no radiation, so there is here. And in the middle, it's something which is model dependent, but it goes from here to here. And this piece is model dependent, but thanks to the formation of the horizon, this continues forever because we are not considering the fact that the energy is that the black hole is losing energy, so it's forever in this sense, and it's really universal. Okay, I have 4 or 5 minutes, right? Uh, so first of all, are there any questions? Then I have one more thing I want to say. No questions? Okay, so I will. The last thing I want to say is yes. Okay, is to set up what we are going to discuss tomorrow and ask you another question that maybe, I mean, it's like that maybe you can think about instead of sleeping. Um, so we've seen something. We've seen the black hole, uh, uh, or like you have this infinite energy creation, right? Because the energy goes like you create energy forever. Of course, this is just because of the approximation of the model. There is no back reaction and so on. But it's still interesting to know how is the energy conservation going to be implemented. This is non-trivial because nothing can escape the black hole, right? So if nothing can escape the black hole, and if the energy can only come from the gravitational energy, how is the black hole losing mass, for instance, right? This is something we can partially discuss tomorrow. The second thing we can discuss tomorrow, not even partially, is the fact, you see, so Pare's diagram are very bad to discuss distances. At late time, you have this constant flux of energy. And when I do this, for an observer on Scale Plus, this is infinite time. The black hole forms on a time scale of the formation of black holes for a stellar mass black hole is a few seconds. So like this is the order of magnitude. When I say form, is I mean, there are subtleties, but anyway, like is the time scale you need to go from a given radius, like larger than 2m, but not so much larger, and to a radius which is very close to 2m. It's something order seconds, right? Whereas all this is the entire history of the universe. So this is very bad in drawing distances, right? But for an observer which is falling into the black hole, like imagine you fall into the black hole, a classical observer, will they see an infinite amount of radiation? You saw all of this traced back. This is infinite here, but this is a very, very short proper time here. So would an observer arrive here and be completely incinerated by this infinite amount of radiation? This is something we are going to see tomorrow. We are going to discuss tomorrow. Finally, one question for you is, we've seen that the spectrum is thermal spectrum. Is this paradox? Is this a problem? Of course, you know the title of my last lecture, but actually think about it. Don't just think about it. It's not like it's good to think about it. Why is it a problem? And how, I mean, like, or why it's not a problem? Like, because it's non-trivial. Like, of course, you know the title, but it's not like having to the problem is something trivial. But is it a problem that the radiation is thermal, so that there are no correlations? Like, you go from a pure state into a mixed state, right? But if you can think about better about why is it a problem, we can discuss in the last lecture. Okay. Okay. Questions? Also on Zoom. You no, sorry. I can finish 1 minute early. Oh yeah, oh, I can finish right on time. I will still.